Good morning, everyone. This is Li,
and I just finished my third year of PhD at
West Virginia University.
today
Today
is both
and
an honor and a pleasure to introduce
Professor Xinlin Li. He obtained his PhD from Dartmouth College in 1992 and became a full professor in 2011 in the Department of Aerospace Engineering and the Laboratory for Atmospheric and Space Physics at the University of Colorado, Boulder. Professor Li's impact on our field of space physics is nothing short of profound. From very early on in his career, Professor Li's work helped pioneer our understanding of the formation of new radiation belts associated with interplanetary shocks and changing the paradigm in our understanding of particle transport. Furthermore, his work has helped us understand the source of MeV electrons in the radiation belts, concluding that they are created through internal acceleration processes rather than from solar origins. Over the duration of his career, he has supervised and guided many well-established scientists in our field. Professor Li has served as a co-investigator of many satellite missions, such as SAMPEX, THEMIS, and the Van Allen probes. He was also the PI of an NSF-funded CubeSat called the Colorado Student Space Weather Experiment, or the CSSWE, which has measured energetic particle in the space for more than 2 years, from 2012 to 2014, leading to more than 29 publications, including 2 in Nature. Recently, he was inducted as an AGU Fellow in 2021. He is currently the PI for the Colorado Inner Radiation Belt Experiment CubeSat mission, also known as CIRBE. Since the launch of CIRBE in 2023, measurements with unprecedented energy resolution, he has already made many profound new discoveries in the radiation belts. So without further ado, please put your hands together as a welcome to the stage, Professor Xinlin Li.
Thank you very much, Gabrielse, for the long introduction. It's probably not the length of introduction is proportional to the speaker's age or experience. All right, good. Now, today I'm going to say, as you see, we are going to talk about the challenge of understanding the variability of radiation belt electrons. Also, we're going to talk about the, my favorite one is the CSSWE and the CIRBE, what they can do. And also what to summarize, at least my opinion, what we can go from here if we really want to quantify the radiation belt electron or energetic electrons, what kind of mission we would need it. Okay, so number one, as you see here, why do we care about energetic electrons? And we say, well, I should acknowledge, probably you read all the names now, mostly they're coming from my former current graduate students and other colleagues. Yeah. So the one is space weather effect, and for the keV, also 10 keV, and then we have the, let's see, I'll try to find the cursor, yeah. Yeah, that could have this surface charging, and then for the high energy, they can have this deep direct discharge. So that has a space weather effect, that's something we care. And also yesterday, we alluded, so we also can have the, IMAG coupling. But then here, just we have to be more careful to say IMAG coupling in terms of the ionosphere current, that mostly energy is still deposited in this 100 kilometers above aurora. This is like a 100 EV, keV or so. But if you have more energetic electron, you can have more in-depth penetration. And then also getting to lower altitude. The thing here is when you get into lower altitude, they are, even though you ionize, but then they recombine very soon. There's not much contribution to the ionosphere current system. So this is another way to show the energy deposition is very energy dependent. You can see like aurora, also the keV is mostly contribution to this E region, but for the D region or below, this for the high energy. Normally, you have a fewer those MeV electrons to get in. Yeah, just total number of particles, they have fewer, but they could penetrate deeper. So another one would be, say, why do we care? This is what we call $300 million questions. $300 million questions. I personally involved at least like 4 or 5 NASA flight proposals, try to determine whether those knocks, they are obviously created by energetic particle electrons, whether they could descend to the stratosphere. And it was pretty well known they will be created by the energetic electrons, but they can recombine with sunlight. UV, they can be recombined very soon. However, if it happen in a polar night when they're not exposed to sunlight, so the lifetime can be extremely long, can be months, and some of those vortex, so they could be descending to the stratosphere. And then if you, again, I just say we had a Don Baker, and Don Baker was 1996 first proposed using the star occultation. So you have to have now this is the Earth, the satellite goes Leo, and then you look in the star has a UV, and the NOx absorbs certain spectrum of the UV, certain line of the UV. So the satellites on the star occultation, they can see the descending of this NOx. And most recently, like Addison Jane as a PI for the MEDEX. So that's all kind of few hundred millions project. So this is important. That's why I say why do we care? We do care. Yeah, so we'd like to find it out. And now you come to the inner manosphere, and the three known populations, and plasma sphere, now it's the EV code, but they're, we'll say they're very important. They're really determining the wave-particle interactions, whether the resonant conditions can be met. Just like really playing the role, they have the most mass. That was, plasma sphere, sometimes used to call part of the ionosphere, just like plasma sphere. And then the ring current carries most energy, and also say anytime talking about the storm, also that's mostly affected by the ring current, right? DST is coming from the ring current, partial ring current. And then the radiation belt, the highest energy, but not so many particles. In terms of total energy, they are not as much as the ring current carries. But nonetheless, they say all this is intermittently coupled or related, correlated, because like, for example, ring current can deform the configuration of the manosphere. Yeah, the ring current. And then the radiation belt electrons, they were only field effect. Their feedback to this field configuration, reconfiguration is negligible. Yeah, but they have their own impact, as we talked about earlier. So in any case, here I would focus on the radiation belt. And here's the radiation belt, and we have the violin probe, geosynchronous geotransfer orbit type, lasting for 7 years. And then the LEO, and then we would have this quite a few LEO satellites, starting with SunPax 1992. And then POSE, and we're going to mention POSE data, and then the CSSW, Firebird, AC6, and Alphen, and then now currently Serbi, and then also Reals to be launched, hopefully soon. Yeah, so CubeSat, they were LEO. So to put everything in context, is the solar cycle-wise, right? And then we combined SunPax measurements starting with 1992, and then combined with CSSWE and the violin probe, and to show your long-term variation of radiation belt electrons, give you an overall picture. Yeah, here I just mentioned about SAA, will be mentioned again. So this picture shows starting from 1992, we plot, this is a solar wind speed, weekly average, and this is sunspot number. So this is more than 2.5 solar cycle. And so you put things in the context, the point here is, has much more activity, much more enhancement of this radiation belt electrons correlating with high-speed solar wind, right? And then particularly during the decline phase of the solar wind or solar cycle, and you see like highest enhancement of the decline phase, the highest electrons enhancement. And also we have the times when you don't have many energetic electrons in the inner manosphere at all. Just really associated with solar activity, particularly solar wind speed. And then the violin probe era, and relatively they stayed in a pretty weak solar cycle, pretty weak solar part of the solar cycle. And then we're going to mention some of this advancement from violin probe measurement, just only some examples. One of that one I mentioned is called storage ring. Remnant belt. If you look here, so before you have this radiation belt here, and then you have a storm coming, and a high L electron, high L being just got lost, and then the newly injected ones, this population, but some of this remnant belt stayed. So this one even got into the published in the science, right? This is to say from highest no, at that time, the very high energy resolution had a clean measurement. And also you can see this, but only lasts for 2 weeks. This only lasts for 2 weeks. Later on, I'm going to show you Serbi has just measured one, lasted much longer. Yeah. And so this is a new belt, what I mentioned. Another thing is from the violin probes, one thing is really the primary drive or charge of violin probes to distinguish the acceleration mechanism. Either they're in situ energized or locally energized or radially transported inward. And so this is one well-quoted figure published in the Science to show this is a good example to indicating, most likely indicating evidence shows the electrons are more likely in situ energized orbit by orbit, right? There's a lot of works follow on or even before. And as we put here, the review papers, the local acceleration process are complicated and it requires a specific chain of events to occur to the proper time scale in order to be effective. And then we'll also another one, say we also have example to show clearly the radially transport inward. So for this example, radially transport inward. And just still a dominant mechanism. Depend on the storm, depend on energy, depend on the each event. So here's another one. It shows this review paper, talk about the more like summarize different local acceleration, transport, and then which one dominating. Also mentioned about the loss, right? When mentioned about loss, you can have magnetic pulse loss to the day side, magnetic pulse loss, or you have like local scattering loss. So now I'm going to propose some question. So because my conclusions here, I just want to say, we really any of this measurement is only a balance of the source and the loss. So for example, you see the measurement here, and you really only thing you can say you measured the balance of loss and source. And then based on the experiments, right? If I ask in your question, which period has more electron enhancement and the loss on these two periods, right? These two periods, which period has more? Just based on experiments, most people, if you studied any radiation by electron, you would say, well, of course, this period has more enhancement, also likely have more loss, right? So this question can be answered. However, the next question to be say, what are the actual enhancements of the electron during these two periods? So this question cannot be answered based on this measurement. Just because what you measured is a balance. There's more loss or more enhancement, you don't know. They can be trade-off, compromised. So the point here is that we know the Earth is an efficient accelerator of electrons. Supposed to be really origin the radiation by electron, hundreds keV to MeV, either come from solar wind originally, but in the solar wind, the energy is only about tens of EV up to keV in solar wind. Another one source has to come from the ionosphere, that is EV, yeah, even lower. And also you can say, well, you can come from the this plasma sheet, yes, but there's also plasma sheets come from ionosphere, come from solar wind, it can be a little higher. Even for plasma sheet, yes, there are still like keV to 10 keV. And also besides for electrons, the ion temperature ratio to the electron ratio is about a factor of 5, depending on the location, can be iron is always higher temperature. Otherwise, how these electrons can be energized to tens and hundreds keV and MeV. So here I'm just say, if you there's no loss, then if you say based on the content what you measured, and you can directly say, okay, this is the source. Right, this is the source. If you just see there's no loss, it's here when it's filled up, and then how fast it's being filled up, you can directly determine the source. However, but once you have a loss, and then you have no way to say what will be the source. unless you know quantify the loss is quantified. So that was my major message, right? And here we only talk about today I'm talking about mostly precipitation loss, but also the losses through the pores is also important. So in other ways, I just say quantitative understanding of the various ionization acceleration mechanism of radiation by electrons fall short. So due to the lack of the understanding of the loss mechanism, you could take it as this is not so optimistic, right? But the fact is we don't know. No one can claim they have really quantified the mechanism leading to the enhancement of the measured of electrons, because we have no idea about how much of them is actually being lost, right? But putting the positively, particularly for young scientists, just say the problem is far from being solved. So much work to do. Yeah, so much work to do. And later on, we're going to show maybe adequate conjunction measurement between the multiple cluster of LEO and the cluster of GTO may enhance our understanding. That's what I'm going to show next. But from now on, I'm going to say what would be a low Earth orbit satellite we can measure. But for the precipitation loss, low Earth orbit satellite would be the best position to make the measurement. So here just says, electrons near equator that have equatorial pitch angle, and then if you have a small pitch angle, and you could reach, to the lower altitude, and if you have a larger pitch angle, you just bounce back in between, right? And then when you're getting close to the lower altitude, sometimes the loss cones like opens up. So that's just like, illustration of the electrons movement. So reality, pay attention to this figure. This is equatorial pitch angle for the L equal to 5. That's only a few degrees. And you have to be like this particle A, you have to be, say, if you are at this, in this red region, they will be lost within a second because it's in the bounce loss cone. In the bounce loss cone, for this like particle A in the bounce loss cone will be lost for small pitch angle right away. And then if you're in the B, in the blue region, that we call quasi-trapped, you are not getting lost right away, but when you're drifting around, they're going to be precipitated in the south attire normally. And that just, they'll be lost within one drift orbit, which is about, say, tens of minutes or an hour, depending on energy. And then if you stay above, like say 4.5 degrees above without pitch angle scattering, and then you can be supposed to be stably trapped. So that is sort of just kind of three populations in the drift loss cone, bounce loss cone, or trap population. And then LEO satellite going to measure all those different populations, but each time they mostly measure one type, depending on location, the longitude, depending on where satellite location. And then you say the LEO measures one of those three populations: trapped, quasi-trapped, untrapped. And so that's sort of the main point. And here, just another way to show, just say, three different population, if measurement, like for example, Survey 51 degree field view perpendicular to local magnetic field line, anytime we measure electron here, they are all precipitating. They're all precipitating. If you measure them, they will be lost within one bounce period, within like they will be lost, precipitating to the southern southern part. If you measure in those region, they'll be quasi-trapped. If you measured in like those region, mostly 90 degree in those region, they'll be stably trapped. This is quasi-trapped. And before I going to show this latest result of the survey, I want to give a brief history background, just say where they're coming from. Because the survey we call it with a reptile 2, so if you say reptile 2, they must have reptile 1, right? And then what is reptile 1? And the reptile 1 is coming from, and the rept, that's to say, talking how many years and effort had spent. So this is in the Violin probe and rept, and then the reptile, and this reptile 1, and was funded by NSF, and it was like many, again, so many years ago, decade ago, and it was started with 2010, that's 14 years ago started, right? And that time we only have 6 channels. Again, this is 14 years ago, we only have a 60 channel, pretty low budget and that time. And then at that time, the way we did it, we handled it, and it's very proudly, 14 years ago, we had a graduate student project class, and the student recruited to learn as they do as they learn. Most of the students, they have to pay tuition, and they get the class credit, but they have to pay tuitions, and they are happy. You see, look at their teeth. They're happy. Yeah, they really gain experience. Many of them become, like Drew Turner here and Quinton. Many of them become leaders in our field. So we train next generation of the scientists and the engineers, right? And so that's the CSSWE, and briefly, and we have total 29, yes, mentioned about the peer-reviewed paper published, and then we also have 5 PhD thesis, at least 1 chapters involved with the CSSWE, and then we also had 2 Nature paper associated with our CSSWE data. And this is a paper by Dan Baker, leading by CSSWE was used as the supporting material. But the other one, we only use CSSWE, and we solve 60 years mystery about the source of the inner radiation belt electrons. So that was published quite a few years ago, based on solely on the CSSWE. So that was a wonderful story. So for a wonderful story, the news media, also student-led, not really, they had mentored by engineers, not professional, but they always, news media always say, student-led CubeSat, satellite fund had a discovery, And I was invited to the Capitol Hill and to share this story, to tell a story, to advocate for more funding to train the next generation of scientists and engineers. And so this is the time that Lauren and Quinton was in the Goddard, at that time. And I was talking to this is a Republican Senator, Cory Gardner, and then for doesn't matter, Republican, Democratic, no one said they're not supporting science, right? When you talk to them, but it's good to show them a vivid examples. So students are trained, great science results achieved, and it would be like to, get more funding to support small sat and the rocket program, etc. Right? And this is 2018, and then in 2019, I was invited by USIA and also to the Capitol Hill, talking about to the staff, congressmen, and also the agency peoples. For example, this is Lisa Winter. Sometimes Chinese say Lisa Winter likes me. That's why, because she also witnessed me advocating for more funding for community. She likes my presentation there as well. So that's about the CSSWE, and now I'm coming back to this survey mission, Colorado Inner Radiation Belt experiment. And we have a little bigger budget now, about 4 million. And we were had this team, about all part-time. Yeah, this all part-time. So Serbia also, this is like say 14 years later or 12 years later, we have much more advanced, more advanced technology. Now we can have like a 129 channel, just very high energy resolution. We have a cleaner measurement. We have also much higher data download. We have a very active, instead of passive, but active attitude control system. We also survived through the pandemic. There's meetings mostly going through the Zoom. Engineers can only go 1 person at a time. Sometimes say, restricted area, only in each lab only have 1 person at a time. Occasionally you have to get permission, get 2, because sometimes the experiment has to be done by 2 persons, but they all had to be get permission to do that. But we survived, and then we're at that time, you see, this is white circles, graduate students, green circles, the undergraduate student. We still have students involved, but the student play more supportive role. They were led by the last profession engineers. So quickly, here's the reptile. We have a similar mechanical design. So the reptile coming to reptile 2, but we have much advanced electronic design. Electronics much more advanced. And so here was so it shows that instrument. Also, we have more money. We purchased the spacecraft from the Blue Canyon technology. So we are purchasing this part. So we focus on the instrument development, testing, and also integration. So that was like just a little more have more money and then like a little more leeway, to do that. So this is like one of the testing. They brought out standing alone and deploy solar panel and deploy antenna, and also we also brought them to the a few miles away from labs to communicating standing alone to communicating with the ground stations, and so this is sort of the attitude control test on airflow bench. Yeah, our PM and project manager and Rick Connors mantra just test early, test often. So we're testing many times. And then we have lucky in the launched on the April 15. Very soon we had like the largest storm in 7 years since like September 2017. This is April 2023, one of the largest storm. And what can you see here is the B is the panel B, 5 snapshot C is here during the main phase. Right here there is the inner belt and the slot region and outer belt, right? Inner belt, outer belt. And then during this storm main phase, you look at this dynamic variation, and then any electron, most electrons above 3.56, they were gone. And there's recovery phase. This is panel D corresponding to here. That recovered, you can see there's up to 5 MeV electrons, 5 MeV electrons enhancement. Then as time goes on, this slot region gradually resume and then gradually resume. Also, after another one, small storm, you can see this is called remnant belt. And then again, I'm going to show much stronger remnant belt after last month's superstorm, right? Superstorm. This one is, small remnant belt. And also we all observe this wisp because the shape, it looks like a wisp. This is a single wisp. Most previous people studied the single wisp because in order to measure the multiple wisp, you need to have high energy resolution. They have the high energy resolution in order to see that. And then so this is a VF wave in the Australia northwest corner here. And this is their station, and this is one person, this is one antenna. So VF wave, the intention is to communicating with the submarine before, not a surface. They can communicate like 50 meters, 80 meters below the seawater, they can communicate. So that was the very strong VF wave. And then they were creating this called WISP. And this is the WISP is a multi-WISP. Here's we observed, this is for the first time, also modeled. Yeah, Zheng Xiang has been doing most of the work simulating of this WISP effect. Again, the reason we can see the multiple WISP is because of high energy resolution. But then we have better understanding from modeling that you have different harmonic wave has to be invoked to create that. So here's another, to me, is also the first time we have seen that's a wide energy range, 0.25 to 1.4 MeV electron cross wide whole entire inner belt and part of the outer belt. This is a measurement. This is smoothed, and then this is the detrended, and that's really called the zebra stripe feature. And again, previous people who have studied them, they mostly focus on the inner belt only, and then not see that high energy. And because if you remember, Van and Probe era, people even debating whether there's any 1 MeV electrons or not. Here we show you not only we measured 1.5 MeV, 1.4 MeV, but also we can see their drift period matching the energy range. So we have this is my graduate student Yang have done this one simple suggestion. If you have any on-site electric field, just like energy change, then you have electrons drifting around, you're going to see the zebra stripe. And so this the drift or drift echoes, drift echo. So this is the one reason, but the exact physical reason, what causes electric field onset, still far from being understood. Yeah, so this is continuing investigation. So another thing from the Serbi measurement, we see the bursty precipitation. This bursty precipitations, I have never seen this myself before, because from like 300 keV all the way to like 2.5 MeV. This bursty precipitation, all those measurement is measured in this bounce loss cone region, in this red bounce loss cone regions. Anything we measure in this red, they were lost within a second. the precipitation. So what causes precipitation, right? Just bursting, just during storm time. Yeah, during storm time. Again, so we combine with the Rossi measurement, which in higher altitude, they measured those cross wave, the kind of the bursty cross wave. Believe it could be a perturbed effect by the UF wave. But measured is like a cross wave, kilohertz, and but they could be affected by UF wave. So that kind of a little bursty feature, but then they cause this bursty precipitation. And so this is also, Jen has done this simulation, the measurement from our survey, and then here's the, so this is a simulation. So that was another feature reviewed by our measurement. Another feature here, just say there were energy-dependent precipitation. Like those one, we believe probably most likely the IMAG wave produced. That's during the active time, IMAG wave produced, because they only supposed to be scattered because the polarity, they only resonant with high energy electrons. Yeah, IMAG waves scattered. So we just have all this, different feature we show example. Another thing I want to mention, survey data, all the year of 2023 is publicly available. The announcement just came out yesterday from the GM newsletter. So people are welcome to, to check this data out, to analyze this data. Now here I'm going to show you the most recent measurement from survey, but to put things in the context, right? Put things in the context. Survey went silent on April 15, just went to sleep. There are some non-flash corruption, then into dead loop. And then woke up for 2.5 days, went back sleep again. So this is like a time sequence. But then they came back again. The survey measurement resumed in this June 15, June 16. And this here is measured pulse measurement, greater than 287, greater than 612. And look at this DST profile, almost like a minus 400 nanotesla, largest storm in 20 years. The previous largest one will be the 2003 November, and then also October Halloween storm. And so this is the largest storm. You can see there was normal feature here in a deep penetration, and then slightly decay. The thing here is though, here we do not have any measurement. So here you can say greater than 600 kVs, okay, greater than 600 kV, some of them decay, and then here's greater than 200, but this is the integral channel. The point here is, what about the rows? Remember, this is about L equal to 3, L equal to 3. What energy are rows? If you form this integral channel, and you just say, okay, this is a greater than the 200 or 300 kV. This is probably greater than 600 kV. But I'm telling you, they are not 600 kV, they're not 700 kV, they're not 800 kV. There has to be a MeV above. So that's what I'm show you next one. And so here's the survey measurement, putting in your contact. Here's the outer belt, and then this is slot region, and this is the inner belt. This is the April 14 measured before it went silent. Outer belt, slot region, inner belt. And this part change with time, right? But also we show you this June 17, a week ago. June 17, we see this blob. And this blob, and if you look at we call this a really new radiation belt. This is after the superstorm. And you look at this, energy is about 1.4 MeV above. Now, say if you say 1.2 or 1.4 MeV, and there's no measurable electrons in the hundreds keV up to 1 MeV, and in this slot region. The physical understandings, they're all being scattered away by plasma hiss, because plasma hiss wave, that's where the slot region coming from. The slot region coming from, again, I want to mention that Larry Land thought 50 years ago had proposed this hiss wave scatter, called this two belt structures, slot region. But when you have these very, very energetic electrons, and the hiss wave not resonant with them, because that will not fit any resonant conditions. So, and also if you know other big storm, and nothing to perturb them, because they will stay inside plasma sphere. And that's where we're talking about high energy and low energy electron. But cold plasma, how they play a role. If you stay in the plasma sphere, all the wave you have is a His wave. You have a little bit maybe penetrating crust, but not deep. And you don't have that IMAG wave. IMAG wave, you need the energy coming from the rain current. So without not a big storm, this would be stay there. And also another thing I'll just say to show you the very detailed, because all this is simulated, we instrument so well understand. We understood the instrument very well. If you see this is a little bit different, L2, that is coming from the proton, also enhanced. This is from proton. And on those proton is coming from about 3 MeV electrons. The cross-contamination is an intrinsic part of an energetic particle instrument. The key is if you know them, which way the cross-contaminating or masquerading each other. But here you can see these electrons, the very low, this part is 1 parts per million. Yeah, look at this dynamic range we measured, log 1 to log 7 dynamic range measured. So another thing I want to emphasize here is they were not going away, but now so far we hope the survey continue update this figure. We have done this for most recent one only a few days ago. And if you find a similar orbit, this part is not going to change. And if you look compared outer belt change, there's some substorm activity. Outer belt change, you can compare with this part. Outer belt change, but not this blob. Just unless you have another comparable magnetic storms, and you can cause that change. So this is what we call another new radiation belt. New radiation belt with long lasting, multiple MeV standing there. All this shape fit the His wave condition. His wave resonant conditions depend on the magnetic field strength as well, right? Magnetic field strength. They can scatter low energy, but they cannot scatter very low energy. They're not going to scatter very high energy. So that was the property of the His wave. Okay. So now just say, well, back to the bigger picture, we say existing issue. Just even though we show your Serbian or CSSW, of course, other like alpha, they all measure those precipitation particles they can measure. However, every time they only measure about the one type, and it's a very limited coverage. So in order to really understand this precipitation, well, I would say we need to have the multiple with high energy resolution. POSE has multiple one, but it has to be recalibrated. That's something I would say when you're using the POSE data, has to be more cautious, very cautious. Say when you give in the greater than this kind of energy, but the reality is the actual energy could be far off. Yeah, as I just showed you here. And then also we said the mechanism responsible for electron, this mechanism is we understand this mechanism, but if you want to quantify them, just not easy. And if you want to quantify them, you have to know both source and loss anodization all play together simultaneously. So one idea we've had is if you have this magnetic conjunction, multiple of them has to be in conjunction, and then you can say we at least understand the precipitation loss. If you for cases where close inside the inner belt, not inner belt, inner manosphere region, inner part of outer belt, not by say eliminating outward magnetic pulse loss, and that in that case still need to combine with modeling. Then you could have a much better understanding or quantification about this mechanism. Otherwise, no matter what you're talking about, your measurement in the transfer orbit, because the loss cone is so small, on only few degree, you cannot simultaneously measure the precipitation and, you cannot measure the precipitation at the same time as that you see the velocity is enhanced, or at least how much is enhanced, how much is precipitated, you cannot tell. Okay, so this is really my last slide, just say the adequate concurrent measurement between multiple LEO and multiple GTO type could enhance our understanding. Thank you very much. Yeah.
All right, we have plenty of time for questions. Student moderators, come on up.
Thank you, Xinlin. So really excited about the Survey data for this recent storm. I mean, in general, the Survey data. And can you go back to your slide that shows the measurement of that? Yes, that one. No, the one before. Okay, that one. So you talked about the proton contamination of the electron measurement around L equals 2-ish that we see. But what about the vice versa? Is that the vice versa? So out at L equals 3, what you're seeing as protons there, that's electron contamination. Is that right?
Yes, and my point is on this part, we measured in the proton channel, but from our Jiang4 simulation, we know there are electrons above 3 MeV. They can masquerading as protons because I have backup slides. Not like, for example, we know this one because above any 3 MeV, they can masquerading as proton. And then for proton between 6.8 to 7 MeV, they were masquerading as electrons. And we have this cutoff. Yeah.
Thank you.
Thanks for the nice citation, and I really enjoyed your summary of the loss processes and how exciting that's going to be for the future. But just adding to what Xinlin was saying is the excitement I think for the future is going to also exist for the energization process, because that's what we discussed today this week quite a bit. The competition, the source due to direct injections, it really hasn't been considered that much, and so a lot of work to be done on the energization. As well as all the wonderful stuff that Xinlin talked about with the losses. So thanks a lot.
Thank you, Larry. But you brought me another idea to try to say is like, for example, what caused these blobs, right? What caused blob? You talk about injection from substorm-related injection. That's one thing absolutely important. But this one could be also due to another smaller scale, like March 91 shock event, like Mario was also advocating. If you have this, can just directly injecting inside.
Xinlin, thanks for a great talk. Also enjoyed the explanations of the loss cones. If you could go back to one of your early slides where you cited a figure from one of your 2021 papers that showed the kind of the entire length of the record that we had. I'm curious about a gap in 2014 during the Van Allen probe.
Yes, coming along.
It's coming. Okay. Well, that might be it right there. That. So, I mean, I think I understand basically the gap between 09, 10, that looks like a kind of a solar minimum thing, but there's this very large dropout, and I've seen it in other slides, but I don't know that anyone has ever explained it. Do you have an explanation?
We have one author like Xinlin Li, who had a published paper. The one explanation is like so weak. Just that time, the solar wind, there's no big storm during that 2013, 2014, very, very quiet. And then the whole outer belt, or another way again, back to the cold plasma spheres expanded, stayed almost constantly around a geostationary orbit. And then you do not have newly injected particles. And then so again, MeV or so, they can slowly scatter by the Higgs wave. Yeah, just very quiet time.
Okay.
Indeed. And also, we also studied, there, even quieter. Yeah, that is it. Because this is like MeV type.
Okay.
But if you plot the low energy, yes, there always, like substorm, you still can have a low energy can go in there.
Oh, okay, thanks.
Yeah.
That's what I was.
Yes, yeah, this is for high energy.
All right, thanks, bye-bye.
Okay, thank you, Xinlin. I'm wondering, I do understand like for your future, what you might want, what new missions you can dream of. I understand the conjunction between low Earth orbit and being out in the radiation belt, but you also had some comments about you also would like to have multi-point measurements from low Earth orbit. And I'm just wondering, what are the main sort of temporal and spatial convolutions or time scales you're worrying about? What is it you would like to see that a single orbiting satellite cannot capture?
Yes, all good, very well. Here I'm bringing up this one, for example. Just for example, say the electrons, this is like a map, right? Here's a map, but electrons precipitating everywhere, suppose, right? But then for the low Earth orbit satellite, depend on particularly for us, if your satellite happen to be in this location, the orbit goes, and the Earth is rotating underneath, right? So every time, depend on our location, say where they were measurement taken, so we can tell whether they precipitating or not. If you have only one satellite and then just say you only have a small coverage, you do not know the global precipitation. If you have multiple ones, then you can tell, combine several orbits. So that's one thing about precipitation.
So basically it's because the Earth is not a real dipole. You need to deconvolute the real shape of
Correct,
it.
inconvolute, right? If it's a
Thank
perfect,
you.
if it's a perfect dipole, then completely different story.
Thank you for the nice talk. This is just for my understanding. When there is a prolonged solar minimum that you showed, nearly the population of MEV electrons are very small. But there are some co-rotating interaction regions during that time, 2008 and 9. Like, can they repopulate the that L shell that you showed in the plasmasphere? Can you just give me some thoughts about it?
Yeah, so that's depend on your co-rotating events. Normally co-rotating, actually they were not, in terms of DST is not very big, but they still could have this continuous substorm injection. You still could have the radio diffusion, and they still could populating, but that I would not call that is a very quiet time co-rotating, right?
Does anybody online have a question? We thought we heard somebody coming off of mute, but just wanted to check if there was someone online who might still have a question. No. Oh, Mary has a question over.
As a comment to the last question, so in 2019, which was dead solar minimum, Van Allen probe saw a co-rotating interaction region in September that produced electrons up to 7.7 MeV because it was a long period co-rotating interaction region. So certainly you can have that. Yeah. In 2019, I'm not sure. Is that
not here, yeah.
Yeah. In there, you're showing 7.7 MeV. At any rate, I showed it Tuesday, so you can have it.
All right, we do have someone online with a question. Do they type it or they want to come off mute?
Hi, David McGaw of Dartmouth. I was wondering what of these observations could be done from the ground?
The observation of the radiation belt, are you talking about?
Yeah, well, precipitation. Would it be visible by, say, rheometers or
yes, absolutely.
missions or the like?
Yes, correct. The rheometers, they will constantly measure the cosmic ray, and then there's a background. When you have substorm injection or storm, then you can see that the rheometer really changed, registered. But the only things if you coming from ground, what you measure is like a collective integral. You will not be able to tell much about the energy spectrum from the ground, right? And also for low energy, they do not reach the ground. They normally their after effect, you could that not reach the ground. The rheometer is not actually measured. It's measured from the ground. It's not really at the ground, right? Not easy.
Yeah, but
yeah.
Well, the other side of it is, would it affect the ionosphere in a measurable way?
Again, well, the ionosphere would say they will, but then just to what extent? We discussed about this one. If you could see this one, ionization, they could reach, but not at the ground. I mean, not directly at the ground, but mostly ionization, ionosphere effect is still higher altitude. Yeah, for example, you can see aurora from the ground, but it's not easy to see radiation bioelectron effect from the ground because they reach lower altitude, they have a lower flux, and then they will be recombined soon. It will be reach lower altitude.
Well, there are various ways of measuring the ionosphere, the state of the ionosphere. Wonder how those measurements could be incorporated.
Okay. Hi, Xinlin.
Thank you.
That's the next question. Okay, so thanks for the nice talk. I'm wondering what's the next step for CubeSats? Because you lead the successful experience with the CubeSat satellites. So what's the next? Because for this one, you have very high time resolution, energy resolution. So are you thinking of constellations?
Yeah, thank you, Xinlin. The one thing here is thank you for bringing this up. For me, I feel confident that for LEO, we have instrument as good as any instrument to make measurement of this energetic electrons. So far, we make measurement of 250 to 6 MeV, but also have developed an instrument measure 30 keV to 600 keV, also with like very high energy resolution, and we can have very high time resolution as well. Right now, we had our instrument can handle milliseconds, but our spacecraft interface couldn't not handle. So that's talking about future-wise. The plan for me is will be hope to, put 2 instruments. You cannot measure wide energy range by 1 instrument. Always statistic in the high energy, in saturation, and low energy. So we can plan to have 2 instruments, called medium energy from 30 keV to 600 keV, and then 300 keV to MeV. That kind of high energy resolution, and also high time resolution. So that's achievable from the LEO low Earth orbit. But for the GTO, completely different story. Just like deorbiting and also radiation harsh environment. So that's much harder. Yeah.
All right, we're going to have one more question. And while that discussion's happening, if the focus group leaders for today could come and line up to prepare to announce your focus group sessions for today.
It's really nice tutorial, and congratulations to the survey team for the really exciting results. Yeah, I just want to add a comment on the effect of the radiation by electrons on the atmosphere, ionosphere.
Yeah.
So using the recent Alphin data, we are able to quantify the radiation belt electron precipitation, and we demonstrate that it can cause the significant ionization down to the 50 kilometers, especially important for the mesosphere. So this paper has been led by Dr. Luisa Capanolo and published in HU Advances last month. Yeah, thank you.
Very good comment. Timely too. I feel a little bit, moderate because from yesterday's discussion,